Hello again. We are now starting the second lecture of this session. It is an honor for me to introduce Professor Kwong Li, Ferguson Professor of Mathematics at the College of William and Mary, Honorary Professor of Mathematics in Shanghai University, Affiliate Member Institute for Quantum Computing, University of Waterloo. He got his PhD in the University of Hong Kong. He is the editor-in-chief of Linear and Multilinear Algebra and the Journal of Matrices and Operators. A professor at the University of Wisconsin from 86 to 88, visiting assistant professor at Johns Hopkins University in 91, visiting professor at the University of Toronto from 98 to 99, chair of mathematics department at College of William and Mary from 02 to 07, honorary professor of mathematics at the University of Hong Kong from 02 to 17. Awarded, you can see the Virginia Outstanding Faculty Award in 04, Simon Teaching Prize for Excellence in the Teaching of Mathematics in 08, Plummer Award for Faculty Excellence in 09, Fulbright Award in 2011, and JMAA Ennis Award in 2015. His general area of research is matrix analysis, operator theory, combinatorial theory, quantum information science, mathematical biology, mathematical education. Some of his work revolves around matrix and operator inequalities, numerical range, preserver, and isometry problem, and quantum error correction. He has been one of the primary organizers of the workshops of numerical range and numerical ready since 92, and workshop on matrices and operators since 07. You can see the list of the workshops on numerical range and numerical ready from 92 to 2020. And at the first time I met Kwong, it was in 2000 in Greece. I think the numerical range is the signature of him. Professor Kwong Li, please. May I ask you open your camera, please? Can you hear me?
Hear me now?
Yes, yes, yes.
Everything good?
May I ask you open the camera?
Yes. Is it good now?
Yes, 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 yes. Thank you.
Okay. Thank you very much. Thank you very much for the kind introduction.
Okay.
Good morning, good afternoon, good evening, everyone, depending on you are in US, Europe, or in China. Okay, so I'm very honored to be invited to give a talk here, and thank you very much for Abbas for the very nice introduction. So one of my favorite topic is numerical range. So today, indeed, I will talk about some recent results on numerical ranges. And this mainly the new result is with Yudong Poon of Iowa State U and Yasu Wang of National Zhongxin University in Taiwan. Okay, so let me with some start with some notation. So I will use, yes, Is it okay? But okay. So Mn is the usual notation for n by n complex matrix. Numerical range, which was mentioned in the talk. I'm very happy to hear that Chapman has some software to deal with this numerical range in Chapman environment. And so it is just the collection of x star ax, where x is a unit vector. So you collect, for every unit vector, you collect a point. So when I introduce this subject to my student or friends, I always say that, oh, using in this digital era, so you always think about this as a digital picture of your matrix. We can talk about operator toward the end, but let me stick with matrix. So you are basically taking a digital picture of the matrix. Every unit vector gives you a pixel, and you collect all these pixels, you get a picture of the matrix. Okay, and so 101 years ago, one of the basic results saying that the numerical range is always a convex set. For matrix, finite dimensional, it is also compact. It's beautiful, if not very useful at all, and we will see some positive and negative aspect of this convexity very soon. But anyway, this is a result that require no assumption on the matrix or even unbounded operator. You can always collect this pixel from the picture, which form a convex set. And so it's easy to compute. If I give you a very simple 2 by 2 diagonal matrix 0, 1, you see that you collect all these pixels, you only get a line segment, including endpoints 0 to 1, even though in principle it is a set of complex number, but for special situation, you get this one. And if you have a diagonal matrix consisting of A1, A2, A3 as the diagonal element, again, you run through all the unit vector, you get this triangle including interior with vertex A1, A2, A3. If you look at the non-normal matrix, 0, 2, 0, 0, this 2 by 2 matrix, then you compute all this, you will find out that I deliberately put 2 here so that for the normalization, you will get the unit disk. So with MATLAB, Chapman, or whatever, this can be easily produced, and you see some simple, nice picture in the simple case. So even for undergraduate students, it may be fun for them to try to evaluate all this so-called sesquilinear form of the matrix. And as I said, you can view it as a picture. And of course, all this illustrate that a line segment, triangle, including interior, unit disk, the unit circle, including interior, are convex set as asserted by the Toeplitz-Kosov theorem. Students always ask, why study? Why do we want to study the numerical range? So I try to convince them that, yes, the numerical range is a picture of the matrix. Why do you want to take a picture of yourself? Because it can be kinds of record, and you can also use it to do something like applying for your driver's license, for your passport, and so forth. So the picture, hopefully, is useful in telling you something about the matrix. So for example, if you see a really skinny picture or tiny picture containing only one point, then you can immediately say that no matter how large the matrix is, the dimension or even operator, it is just a scalar matrix, and the scalar is exactly the point you see in the picture. Again, if you see that it's very thin, like our earlier example, it is just a subset of real line on the complex plane, then you can immediately conclude that you are talking about a Hermitian matrix. And in fact, in some more general Banach space setting, this will be the defining property for Hermitian or self-adjoint property. You can also detect positive semi-definiteness by checking that the numerical range always from 0 to infinity on the non-negative real line. And one thing is that it always contains the eigenvalues of matrices, or in general, the spectrum, if it is infinite dimensional operator. So it gives you a containment region But this is not a very good containment region. Actually, it was criticized by people saying that, wow, you have this convex set. Look at this 2 by 2 matrix. Eigenvalue obviously is 0. But when you look at the disk, you can do a calculation and show that the numerical range is the disk with radius m. If m is large, you get a huge set containing this tiny spectrum. So it is not very good. Okay. So in some situation, you don't want to do that. Nevertheless, if this thing is available, this picture is available, just in case you see that, for example, it is on the whole numerical range is contained in the left half plane, then you can conclude that A is stable in differential equation, for example. If you see that the numerical range is strictly inside the unit circle, then we know that AM will converge to 0 as M go to 0. So using it as a tool to do spectrum containment region may not be a very good thing, but if the picture is available already, then sometimes you get some information for free. Okay? And in fact, I would argue even more. We create a tool to study the matrix, but sometimes the data are free in the sense that when you look at, for example, in quantum information science, quantum mechanics, the collection of this X star AX, or treat it as trace AXX star, the outer product of XX star, can be viewed as a measurement of a pure state. But the convexity, it is actually the collection of all the quantum state by the observable associated with a self-adjoint matrix A, for example. All right, so in the lab, you collect a few data. You do not, it is hard to create all the points, right? It's an infinite set. But if you get 10 times measurement by random, however, you define random unit vector, you always see a point. Then you should be confident enough to see that the observable behind is just a scalar matrix. If you're talking about two observable, put them together, A1, A2, and put it as a complex matrix, do the joint measurement, you always see a real line, then you see that one of the observable are actually useless, always give you 0, things like that. So even though, for example, talking about the containment region of spectrum, it is not very effective, but sometimes as a byproduct, or sometimes using the given information available, you can still gain something. Okay, so for example, for eigenvalue perturbation problem, it is very hard to use the eigenvalue of A and the size of the perturbation delta A to estimate how much the spectrum change. Numerical range is not a good containment region, but it does satisfy the entry-wise set addition. So you can use this if you know WA, it contains all the eigenvalue. If you perturb A a little bit, then the numerical range will not change much. In some situation, you may get a good estimate for that. Okay, but once again, I have to make the disclaimer that no, I would not say that this is a very good thing to a good tool to deal with the spectrum containment. But really like the talk of Nick very much, and also of course Rajendra, we talk about, for example, geometric mean, we talk about harmonic mean, we talk about the usual, right, average mean, arithmetic mean. So the tool can be used in different occasions. Sometimes when the tool is not available, like the continuous linear algebra concept, then we create a tool to overcome the hardship that the basic tool is not good enough. So exactly like Bauer in 70s criticized that, oh, this numerical range definition using the Hilbert space definition do not give good containment region for spectrum. So he used the Banach algebra setting, looking at all the linear functional and the vector in the Banach space. Norm 1, the pair gives you 1 when you add fx on it. Then that thing will give a better containment region. And hopefully you can improve that by modifying the definition, creating your tool so that you get a better method to, for example, if your aim is to estimate the eigenvalues. So this is somewhat related to the earlier talks and also related to what I'm going to tell you, the story about this generalized numerical range. So far, so good? Okay, so let us move on. So let me pinpoint at a very special property that interests people, which is the normality. So we know that if A is a normal matrix, which means that it is unitarily diagonalizable, then the numerical range A is just a convex hull of the eigenvalue. So it is a polygon. This is actually true again for operator. Then the closure, you have to take the closure of the numerical range as the convex hull of the spectrum. So when people see the picture of a normal matrix is a polygon, of course they want to ask the question, how about the converse? Wouldn't it be nice that if you look at the picture, you can identify the matrix or the operator is normal by looking at the picture of the numerical range? And go back to the quantum mechanics example, sometimes it's not that you can generate all the points. The matrix is not even available, but you get the measurement of that matrix or operator behind the model, and you look at the picture and you want to get some conclusion what is behind the system. So it turns out that unfortunately the converse is not true, and you can have some kinds of pathetic situation that your operator or your matrix A actually up to unitary similarity, it consists of two parts. One part is a diagonal, so part is a normal matrix in some sense, but the other part is completely out of control. So for instance, your matrix may be a 5 by 5 matrix up to unitary similarity consists of this root of unity as eigenvalue and a non-normal part like this. Then when you construct the numerical range or see the picture of this 5 by 5 matrix, you only see the triangle with 1 omega omega square, the 3 primitive root of unity. Take the convex hull, will cover the thing inside. So there's some hidden thing you do not know. And I find it quite amusing, right? So in many scientific study, you look at the obvious evidence, you want to draw some conclusion. However, there's something hidden that you need some more study to uncover the truth. Otherwise, you will be misled by thinking that, oh, this is basically a normal matrix with these 3 distinct eigenvalues, which will produce this picture without realizing that there's some hidden thing there. Right. So this phenomenon requires enough dimension to hide the dirty thing inside. So for 4 by 4 matrix, then we are okay. There's no room to do this kind of trick, because in general, you must have a normal part, right? 3 vertex or 2 vertex degenerate to 1 vertex. So the non-degenerate case, at least 3 vertex, to hide something non-normal, you need another 2 dimensions. So that is why once you go down to 4 dimensions, there's no room for you to hide this. Another result is that if you have enough vertex point, turn out that every vertex point of this polygon must be a reducing eigenvalue. Not only an eigenvalue, but also the row and column here, the eigenvalue will sit right at the diagonal entry. So when you have n-1 eigenvalue identified as reducing eigenvalue, there's no room for things to go wrong. So these are some special case. So good, not so good. Just like the example of a spectrum containment region. For normal matrix, we may be able to rule out something is not a normal matrix, namely when it is not a polygon. Sometimes, if we are lucky, we are talking about 4 by 4, or there are many, many vertices, distinct vertices for the normal matrix. Then we can also get some conclusion. All right? Then it comes to my earlier comment that as a researcher, theorists, or applied people, you want to create or modify or sharpen your tool to make the test better so that you can get some conclusive statement about the normality, for example. It is almost like our COVID-19, right? So you have some old tests, it doesn't quite work. So of course you have to derive new tests to do that. So what are the new tests we are going to derive to deal with this? So it was the concept of K numerical range. So sort of you can regard it as a refinement of the first level picture. The first level picture only involves 1 unit vector, So this high resolution camera require k unit vector which form an orthonormal set. But then you mix them to get a number. You get the k vector orthonormal set, and then you compute the quadratic form or sesquilinear form and sum them up. Okay. Or if you group all the unit vector as a n by k matrix, you are computing the trace of x star ax. Okay. So it was a concept raised in 60s by Hamels, and Berger proved that, well, again, you like it or not, people care about the convexity. It turned out to be a convex set. And then a decade later, so Marcus, Moyes, and Filipenko used this concept. Well, Berger deal with the operator situation. So Marcus, Moyes, and Filipenko in 78 bring this into the study of normality problem, or study some, try to extend some basic result to see whether this so-called, if I call it high resolution picture, would it bring us more? So at least it capture the singleton situation. If this picture is just a singleton, then after normalization, it is a scalar matrix, right? So you have k copy. That is why it is mu over ki. If you see that this picture is a line segment, not necessarily a real line segment. Well, actually, this is also true for the classical case when k equal to 1. Obviously, when k equal to 1, we go back to the classical numerical range. Then you can see that, oh, this is basically Hermitian, in the sense that your matrix, complex matrix A, is basically a translation alpha I plus beta times a Hermitian matrix. And good news is, for normal, we also have the forward implication that not only one numerical range, but the k numerical range will always be a polygon. Vertex are actually always the sum of k eigenvalues, matrix A. But at this point, we still do not have the desired situation that looking at the picture, you will know what happened. So in the same paper, they show that, if one test is not good enough, then I can do n-1 test. By the way, when k is n, then you just get trace of A, which is the singleton. So we always consider k numerical range from 1 to n-1. So they said that, if you check whether the matrix A is normal, or like what I said, well, check normal, you check A star equal to A star A, but assume A is hidden somehow. We only get the measurement or the picture of the k numerical range. But if you are able to get all this data from this set of data, the different picture, k from 1 to n-1, if all of them are polygon, then I can say that it is normal. So I saw this paper when I was a graduate student and see that, oh, quite nice. So you can modify the tool to achieve your goal. But something not quite satisfactory is that I make the joke about COVID-19, right? So now I said that if you take 1 up to n-1 so many tests, you can determine whether something is normal. Yes, better than there's no test. But is it possible to use only one guy? The first observation is you can cut down the jobs to 1/2 of that because of this identity. It turns out that k numerical range and n-k numerical range are related in this way. This is just a translation by trace A. You can get the information of the other. For example, if you check 1 up to n/2, it is polygon. And using this formula, you can see that, oh, every k, the thing is a polygon, and we can get the normality conclusion. And then, so we don't need to do more than n/2 so many tests, which is an improvement. But as a mathematician, you want to further trim down, cut down the testing. Can I just do one test for that? Of course, W1, the classical numerical range is a polygon does not ensure the thing is normal. So we have to select K carefully. If you are only allowed to do one test, and you determine that, what test should you do? It turns out that exactly like the idea of resolution, the more unit vector involved, better information you can collect. So, and also by the duality here, you do not take n-1 so many orthonormal vectors because it is just the same as taking one. So turn out that like the binomial coefficient, the K which contains most information is the one near n/2. Okay. So when n is even, you have three guys satisfying this one, n/2, n/2 minus 1, n/2 plus 1. There are three things you can try. If n is odd, you can try n minus 1/2, n plus 1/2. And if you check this guy, just check one thing. You see a polygon. Congratulations, you get a normal matrix. And if it is not normal, that will definitely be reflected by this particular K. So pretend, right now I'm working with the quantum information scientists. Every time we have a theorem, we ask, in the lab, can we produce a set up the apparatus to do a test like that? So this tells us that indeed you can selectively set up the apparatus to check the K numerical range, and one picture tell you whether it is normal. But again, as a mathematician, we want to know, well, after all, why it works. In general, why it doesn't work for smaller K, and then we can actually extend the result about the basic structure. So in general, if you have no choice, people just show you a picture of W2A is a polygon, for example. What can you say? And we say that, oh, there's still some intrinsic algebraic or analytic property of the matrix A. Namely, you can still extract a subsystem. A, the matrix can be decomposed up to unitary similarity. You can extract a diagonal matrix D, which always produce, remember, WKA, if K, D, the dimension is large enough. In this case, I require it to be larger than K, so that it makes sense to talk about the K numerical range. Then that thing will always be a polygon, and the rest is always the hidden guy. Okay, so that is how we follow up the earlier result and sharpen the two so that one test is good enough. Any question at this point? Okay, so now something is wrong. My title said commutativity of matrices. Where is the commutativity? Well, of course, commutativity talk about more than one matrices. So we cannot just take a solo picture. We have to take a group picture. So, and the concept come up, the John numerical range. Well, don't misunderstand, we do not create this concept for this study. It is useful for this study actually in control theory or in even quantum mechanics. When you talk about the John measurement of more than one observable, this comes around quite naturally. But anyway, let me just look at the John numerical range. Of course, it goes from classical John numerical range, but let me quickly jump to the high resolution K numerical range. Very simple. You have a bunch of matrices. I just take the same pixel, right? Use the camera to take a snapshot of all this A1 up to AM. So for every choice of this partial isometry or X consisting of all this orthonormal column, I take the trace. So I get a number. Each number is a complex number, so I have a set in CM. So the question is, now, if a solo picture is good to study the matrix A or operator A, the group picture, would it tell us something good about this collection of matrices? Yeah, again, sorry I'm a big fan of this Turpin-Southall theorem, and many study. The first question people always ask, John numerical range, is it a convex set? Unfortunately, once you go beyond one complex matrix, if you have two complex matrix, it fails. It fails to be convex. So that thing is not so nice for people who like convexity. So here I mentioned that I have to apologize. Some people care, some people don't. It's okay. But how about this group picture? What can we say? Now, this is not a big theorem. It's just an observation, quite easily extending the old result, saying that, oh, how about this group picture collapse to a singleton in Cm. So you get an M tuple of complex number. No matter what you put there, you always get the same point in Cm. Then it turns out that this group of matrices, each of them should be scalar. Of course, they commute. Another situation is that in Cm, just like the multivariable calculus in Rn, you can talk about a straight line in Rn. So you regard the geometrical structure of a Cm set is R2m, right? So 2m real dimension. You can still talk about a line segment because it is a complex set. It is not convex, but it turns out that if it lies on a straight line, it must be a line segment, must be connected. The connectedness guarantee that it will give you a line segment. So interesting enough, again, you can say that all this A1 up to AM is basically a Hermitian and root from the same Hermitian matrix H. So each of them will be just a different translation and scaling of a same Hermitian matrix. Of course, then you can say that they form a computing family. So these are the highly degenerate case. Of course, we are interested in more general situation. So turn out that it is the same as the one matrix situation. And actually, even when we have one matrix, we can say something that, remember, when K is really close to n over 2, we check the one numerical range of one matrix, it gives you a normal matrix. It turns out that if you have m matrices, you take this group picture, and you can decide that this m matrices actually is a family of mutually commute normal matrices. Each one is a normal matrix and they are mutually commuting. And there's some here. And also, how do we look at the picture and decide that? It turns out that it is an extension of the polygon from the complex plane, which we call a polyhedral set. So it is always bounded compact for matrices. So you only need to check that it is polyhedral, meaning that it is a convex set of finitely many vertices, or it is a compact set formed by intersection of a finite number of closed half space. Okay, maybe look at the vertex idea, it's easy. So it's just a finite number of Cm, right? You have a point, all these many points in Cm, but finitely many, you take the convex cell. So it turns out that if you can have access to this one and see that, oh, okay, this guy, take a group picture, it is always a polyhedral set. But be careful, you have to take your really high resolution picture, K very close to n over 2, then you're okay. But this equivalent condition, one of them is easy. You look at the picture. This one is the simplest test. Only one single K can get you the conclusion. E is an imitation of the result of markers. And or they say that you can check everyone is true. Okay. So for every K, and you can only check one K, but here come to the graphic. So in application, who in the world can construct a picture in Cm, right? Even C2 involve 4 dimensions. It turns out that all we can do is to look at A1 up to AM and only check 2. So you said, hey, Kwong is still in C2. And I forget to mention another thing is you can always break A1 into the Hermitian decomposition H1 plus IG1 up to AM equal to HM plus IGM. So you get 2M Hermitian matrix come around from the Hermitian part and skew Hermitian part of that. Now you look at this 2M guy. Every time you just put two together and check the numerical range, which now become a two-dimensional picture. So every time you check that, 2M choose 2 out of that, if it is always commuting or give you a polygon on R2, then you can get the conclusion. So this actually, when you think about the commutativity condition, is really a matter of two matrices, whether they commute. Mutually commute, you pick arbitrary 2D commute, and there's a basic matrix theory theorem, no matter finite or infinite family, it is good enough for you to conclude that the whole set of matrices are simultaneously diagonalizable, and therefore they are commuting normal matrices. So you can actually deal with a family of matrices, and all you need to do is to check any collection of them. They form a polyhedral set, the K numerical range, or you just check a maximally linearly independent set. So in a sense that you get a commuting subspace of matrices, of course, you all only need to check the basis. And the most stingy way is the following. You give me an infinite family, I find a maximally linearly independent set, which is a basis for the span of F. And we just take the highest resolution picture and check that guy is a polyhedral set. If it were, then the whole family is a commuting family of normal matrices. If not, it is not. Okay? And also go back to the earlier theorem or the remark I made. If it is too difficult to look at a subset of CM, you can look at two matrices at a time. Do more work, but you can determine the pictures. And then, usually, working with students, the next question will be, hey, it's fun, only this Kwong Li crazy guy like this kinds of commuting normal family. What is it good for? So, for some other subject like representation theory, sometimes you can get a easy unitary representation of a family. Now, once you get a family, you can check whether using, well, I would not say that you have to always use this tool to do that, right? But sometimes, maybe some data is easy to collect. Maybe there's an easy unitary representation. Maybe it is easy to see. So under all this, if you have this free data to analyze, then you look at that, you say, I can check this unitary representation, finite dimensional, actually, using the numerical range test. It gives you a commuting family. Then it is not decisively tell you that the original group is a commutative group, abelian group, but at least there are good evidence to show that. Or turn it around, if you look at a unitary representation, it failed to be a commuting normal matrix. Of course, the original group will not be abelian. More generally, as we know, finite dimensional matrix group or bounded group, up to similarity, you can find an invertible matrix S to turn it into a subgroup of unitary group. Then you can also apply this trick to show whether the bounded group of matrices actually is or at least not a commutative group, right? Or if you take the whole group and do this similarity, then you can exactly use the PVA theorem to check whether it is an abelian group. So my recent interest is in this quantum computing. So there's something called SLAA channel. So it is a quantum operation can convert some quantum state. Mathematically, it simply says that you use the SLAA map, which you select a correlation matrix, which is a positive semi-definite matrix with diagonal entry equal to 1, and you do the Hardeman product or entry-wise product, define the map like that, then that is what they call a SLAA channel. Again, student immediately laugh, hey, Kwong. Look at the map, the definition, you can tell whether it is of this form. But do remember, when we use our math theory in practice, very often the thing is behind the scene. We actually do not know the quantum operation. Who knows? The nature gives you a quantum operation. Your lab produces a quantum operation, interact with the environment. What can we say about the quantum operation? So it will require a lot of tests to know that this can be assumed to be of this form. But a recent result says that there is something called the Krauss operator associated with the channel. And if you have the channel, you can do some experiment, so-called quantum system tomography. You get some information about the channel, and you test those Krauss operator on the operator system. So and it is quite common to get in quantum mechanics to get the measurement of, for example, the classical numerical range, joint numerical range. If you just happen to see that, this form actually a commutative set, or very likely to form a commutative set, then you can narrow down your experiment to test whether it actually is a pseudo channel. Okay. And also there are some very, in some sense abstract kinds of distribution function in quantum mechanics. So it, depending on a rho and a given bunch of Hermitian matrices to them is always observable, then you can construct a distribution function, whatever the use of that. But again, it is interesting that it turns out that if you get a full rank density matrix or quantum state, and if you use M observable to form this distribution function, either you look at the function or you look at the observable or the matrices A1 up to AM, it turns out that there's a close connection between them. So again, I would not say that that is the tool to study whether a Wigner distribution function is positive or not, but if it happened that you get information about positivity, you get commutativity, and vice versa. So there are some, if people are interested in something else, instead of this crazy guy like me doing all this numerical range study, so that is some other direction. Okay. So we talk about the family being commutative. Of course, we will not escape the question of if we only know again, doing research, right? We want to create our tool so that we can tell everything. Okay, so give you all the n square entry of A1, all the n square of AM, then you examine, dissect everything, and then look at that and multiply them and do reduction on them, see what happened, right? But the thing is that if you do not know, it is not given. You only get partial information, some measurement, some data associated with it. So in my talk, I always say that, give you some group picture of that. So in the earlier result, it says that, okay, if we know the picture of high resolution K very close to n over 2, then we get the normality. So what happened? What happened? If we are given, you have no choice. The data available is some joint picture of K numerical range, low resolution camera. What can you say? I guess smart audience would be able to guess that exactly we can get a subsystem structure. So you can find a common unitary to reduce every matrix A to a direct sum of A, basically normal or diagonal matrix, and something which do not show hidden in the picture in the polyhedral set. So if you think about polygon, then it is something hidden there that we cannot extract information. Okay, it's not the ideal case, but at least you know that there's a subsystem like that, and it's quite interesting. The paper was accepted by JMAA, and then the referee pointed out that one big improvement we have done is that in the one numerical range case, we only know that the D matrix will be at least of dimension K or bigger, bigger than K, so that you can talk about K numerical range. But in our result, we said that actually it's double the dimension, at least 2K, so that we get this thing happen. So we always look at a K less than or equal to n over 2. If indeed the group picture is a polyhedral set, then we know that you have a common unitary to reduce everything to a subsystem. so that it behaves like commuting normal matrix, which are diagonal matrix. And there's some hidden information you cannot get. So if needed, if you're desperate about understanding the matrices behind, then you have to derive some more tests to extract the information of QJ. Maybe you use a larger K. Maybe sometimes there's some way to reduce the problem so that you don't need to worry about DJ and then just go directly to QJ. You choose, for example, for mathematics, it is easy. You just look at the compression of the matrix on QJ. Refuse to use unit vector or for normal vector associated with DJ, then you can extract information of QJ. But anyway, that is what we can say. If we are given a K, we know that. Okay, and actually, you do not go down. Once you know that the K numerical range is a polyhedron, then or polyhedral set. So for smaller L, you look at low resolution picture, will not give you additional information. That K will tell you everything. You always go up. So basically, it's an extension of the old result, and we also have this kinds of extension. Okay. So as I said, you can always do it as a subsystem. So turn it around. If you are doing control theory or something, if you want to achieve those measurements, then you can, I mentioned that to detect whether QJ is also commuting diagonal matrix, you can restrict your attention to orthonormal vector orthogonal to those in the basis of DJ. But on the other hand, if you want to achieve something, why bother going to look at this hidden part? You can always go to the subsystem to extract whatever measurement or information you want. Good. Okay, so let us move further. So if I use K numerical range as a sort of choosing camera, so I develop camera from the classical John numerical range for group picture, tool numerical range, and so forth, then we find useful. But how about I can do something even more flexible? So, well, even when I was a graduate student, I asked the question, why people consider all these different generalized numerical range just for publishing paper or something? And now I turn my view a little bit different. Actually, it's not that they want to, for the sake of generalization, to generalize. And it's exactly how we sharpen our toolbox, so that we can extract or get more useful information for the problem we want to study. So at this point, if we have the K numerical range camera for us to use, among other problems, but for commutativity problem, we can use that to detect the group of matrices being commuting normal. What about we can construct even more powerful camera? Again, I make the joke on the current issue, COVID-19, right? So we can construct these kinds of K numerical range to detect commuting normal matrices. But how about constructing something simpler or more special and more effective tests? So it turns out that there's a concept, again, it's not invented by us, but other people ask the question, and very, well, in some sense, very natural. So one numerical range is look at the behavior of the sesquilinear form on a matrix A. K numerical range is to look at K unit vector from an orthonormal set to look at the sum. How about like many problems in statistics in many areas? Not all vectors are equal, or not all quadratic forms are equal. Some are more important, so I can give some weight, okay, to the sesquilinear form. So I select my test on x1 up to xk, but some x1, x2, x3 has some different weight. So I associate with each xj star a xj with a cj and sum them up. If my C vector is just the 1, 0, 0, 0, 0, 0 vector, of course we go back to the classical numerical range. If I'm talking about C equal to 1, 1, 1, 1, k of them, and bunch of 0, then I go back to the K numerical range. But because of the question itself asks for a weighted sesquilinear form, or perhaps this flexibility allows us to extract more information about the matrix or the family of matrices. Wouldn't it be nice? So people look at that and see what happened. So it turns out that, yes, indeed, it will simplify this test substantially if you can indeed get the information about these weighted kinds of numerical range, the C numerical range. You do not look at the whole picture. All you need to do is to detect whether there is a so-called conical point. Roughly, conical point is this set may not be convex. You take the convex hull and see whether the convex hull have a point behave like a vertex point. You can find n, if it is in cm, you have to find enough independent support plane passing through that. So an ice cream cone, the vertex is a conical point. A polyhedral cone, a vertex will be a conical point. Okay, so if you do such a test, you can localize your picture, zoom in to see if you are lucky enough to find one conical point, and which usually occur at some extremal situation when you apply some linear functional to this set of data. So if you look at this picture and somehow, like simplex method or whatever, if you have, when you collect the data, there's a way for you to go to the extreme situation, and if it turned out to be one vertex only, you don't need more, right? Then you can immediately conclude that A1 up to AM is a commuting normal matrix. So it's a little bit technical, but when you think about that, when I get a very good picture, one point is enough to detect the commutativity of the set of matrices and they are normal. Then again, I can ask the question, if I give you an arbitrary C, so you go to the camera shop, the only thing available is this one. So people give me this C camera to do the C numerical range picture. Then what do I expect? What do I expect when I examine the picture? What kinds of conclusion can I get? So it turns out that I look at the manual, the C numerical range, of course, the weight will determine how powerful my camera is to extract information about the collection of matrices. So I have to examine, actually arrange the entry in descending order and examine the inequality case. It turns out that if I find that something very close to n over 2, you get an inequality. Or you, from the smallest to the biggest one, again, you see an inequality like that. Remember the duality. Here we also have the duality. It turns out that you go from 1 up to n over 2, or n over 2 up to n, if you identify inequality as close, and we remember, close to n over 2 is the important thing. So when we find the inequality closest to n over 2, then looking at the manual, if your C numerical range have a C equal to this one, then I can extract subsystem property. Take a picture, I get a polyhedral set. Now remember, this may not be convex. So if I say it is polyhedral, I implicitly assume it is convex. But turn out that it doesn't matter. If you check the convex hull is a polyhedral set itself, you can not miss anything. You will get the convex set. And then that is exactly our subsystem reduction. And you will be able to extract a DJ, normal part or diagonal part with something hidden part. And the C numerical range depend only on this D1 up to Dm. And the group of entry from some of them are sort of useless, will be absorbed by this useless part, which will not reflect anything. So your camera, up to that resolution, this is the crucial number, tell you the important information. But once you know that this guy has this D1 up to Dm part, so for any other camera, you will exactly get a polyhedron as long as this resolution level, checking this inequality closest to n/2 is not as close to n/2 as the original camera, then all other picture will be polyhedral. So again, thinking about in the lab, if you want to design some experiment to improve the situation, you have to choose a camera so that you get an inequality closer to n/2. Of course, if you use K numerical range, then you use K even closer to n/2. If you have all kinds of camera, then just go to choose a C so that it will give you better information. Okay, so my time is almost up, so I will conclude by saying some further research ongoing project. So of course, almost like following the comment of Nick, after you have this discrete finite situation, how about general operator infinite dimensional? Okay, may be separable, may not be even separable. So suppose you have a bunch of operator. Can we say something clever? If we take a picture of that, it's even harder to take this infinite dimensional operator's picture, but assume somehow you gather the information. Okay. As I said, sometimes you get a local part or you get some data, you already can get some conclusion. So suppose you have the machinery to take this picture and it is polyhedral. Turn out that we can extend some of the result. If you look at the closure, because in the infinite dimensional case, the C numerical range is a bounded set but may not be closed. So we take the closure so that to use the compactness. If you do not use the closure or you use the closure, it will be connected to the essential numerical range. You have to do some perturbation, finite rank perturbation. And some people have experience with infinite dimensional operators numerical range. Is not surprised to see that you will run into this essential numerical range, which is the numerical ranges of the compact perturbation of the operator. And of course, this kind of study is related to the Coquen algebra associated with the BH. So you use BH mop out all the compact operator, and then you can use this numerical range idea to sometimes get some useful information about the geometry or some behavior of the Coquen algebra. Something I mentioned only Bauer field of value, that there are also this version of the numerical range on general Banach algebra, and there are many interesting questions there. John numerical range has been studied. Convexity is not known, for example. In general, not convex, even for one operator, right? I'm thinking already about the essential numerical range. Surprisingly, is always convex. And this one, how about John numerical range of several Banach algebra operator? That is not known, and no an example for non-convexity. But maybe I should not emphasize so much. So maybe interesting, maybe not so interesting. Anyway, so I think it's a good time to stop. So hopefully, if you're interested in this kind of thing, I will be able to find more results, or you can help me to solve some problem that I can tell you.
Thank you very much. It was a very nice lecture.
Stop here.
Is there any question or remarks? You can write down in the chat box, or you can raise your hand. We will open your microphone, and you can talk. Okay. Chikon, can you see the representer node on the right-hand side of your screen?
Right. Yes. So suppose WK is a polyhedral for your special K. How of any two matrices still Hermitian part, we can conclude that. Oh, okay. That actually is because of the we know that if you have a family of matrices, any two of them commute, then the whole family will commute. So I think maybe in Horn and Johnson topics in matrix analysis, maybe there's a proof or the first volume or second volume. It's quite a nice proof. So originally, you have finitely many, then you can find a common eigenvector and then reduce it. But if you are talking about Hermitian, then after you reduce it, it becomes diagonal. Now think about the normal and Hermitian. It's really a normal matrix. It's the Hermitian skew Hermitian part is commuting. So we extend, or when I said everything about complex matrices, when you think about, put it back to the context of Hermitian matrix by looking at the Hermitian skew, Hermitian part. I'm really talking about any two in that family. I break A1 into H1 plus IG1, H2 plus IG2, and so on and so forth. Actually, many things hinge upon this observation that if two of them commute, then the whole family commute, and therefore you glue it back to the A1 up to AM, they form commuting normal. What I'm hiding is, actually there's another surprisingly recent paper inspired by Professor Müller's question. If I give you two commuting, not necessarily normal matrix, would the numerical range, John numerical range be convex? And the answer is no. So this polyhedral property, having vertices and so forth, turned out to be a crucial thing in our study. Okay, I hope it's okay, so you can further ask questions. I look at the second one. What is QJ in the theorem in C-numerical range? Right, so remember the first result saying that if it is a polygon, remember the 5 by 5 matrix, we have a 3 by 3 normal matrix, direct sum with a 2 by 2 non-normal part. So this is exactly a extension of that result. It turns out that for the whole collection of A1 up to AM, if you see that the C numerical range is a polyhedral set, but your C do not have that high resolution, for example, C go back to 1, go back to 2, and all you can say is that all those AI, you can extract a commuting normal part, which is your diagonal matrix, and there's some hidden part, QJ, you get no information by looking at the C numerical range. Right, that is that idea. So we have no control by studying numerical range. We have no control, no information about those QJ. If you want to know more, you must do some more tests and do some other.
Is there any more questions or comments?
Study the collection of matrices.
Okay.
Oh, I see the question, sorry. So it's the typo that I write BQJ and then it becomes BJ. Sorry about that. Yes, I see. I was trying to answer. I have a typo and then what is the QJ, right? So this will become BJ and QJ. If I set it up, where do I set it up? QJ. Somewhere so just assume QJ and BJ are the same guy. Those are hidden. Sorry about that. Right. I see many friends.
Thank you very much welcome
for coming to my
this
talk.
session. Thanks for coming.
Yeah, good to see you.
You can open your microphone. You can talk, Boardman. Okay. Thank you very much. Okay. Thank you.
Yep, I agree. Completely agree with Hugo's comment. Yes. Mm-hmm.
If anyone's talk, we will open here or his microphone. Okay. If there is no questions, we should thanks again, Professor Kwong Li, for a very nice lecture. Okay. I should thank myself.
Thank you very much.